Okay. All right, so you should be able to see both PowerPoint first slide and myself somewhere in there as well. Slides are more important. Okay, want to welcome you all to this book launch event. My name is Terry Stratoudakis. I work for ALE Consultants. This book launch event is to introduce a book that that is just being released that I just wrote. The book title is Introduction to LabVIEW FPGA for RF, radar, and electronic warfare applications. So one thing that's we've observed is that there is a need for FPGAs in RF, radar, and electronic warfare applications. FPGAs allow us to create and develop proprietary disruptive solutions. They are an alternative to ASICs, and they allow for modular instrumentation. There's the Association of Old Crows has a monthly magazine that comes out. It's called the Journal of Electronic Defense, and in their February 2020 technology survey, there were many manufacturers and products in that survey that had FPGAs, and not just one, but multiple FPGAs in some cases. And you can see the quote there from the magazine, from this particular issue. Now, when we look at the technology, traditionally what was used was, if you needed custom hardware, we needed to have an ASIC, which is an application-specific integrated circuit. And the idea of an ASIC is that you can make your own hardware, your own integrated circuit, but just that with an ASIC, there was a really long lead time. Right? It needed 6 to 18 months. And because you had this long lead time, you would try to make many ASICs, so that way that particular run, you could amortize the cost over the different products, the different items that were ASICs that were built. And also another big challenge with ASICs was that you had to wait 6 to 18 months. So anytime you needed to make a change, you'd have to go make new ASICs, unless you had predicted that issue or change. Whereas in FPGA, the F in FPGA is field, and the P, of course, field programmable, FP. And so the idea with an FPGA is that you can have just one of them, and you can reconfigure it and essentially reprogram it so that it can serve a different purpose. And this chart here shows that with the ASIC, there's a higher entry cost, let alone the time. It's not even showing in there. And another benefit with FPGAs is because they're reconfigurable, you can have platforms kind of like the NI platform, which of course the book centers around, and we can have a modular configuration. And by modular, we mean that we can have different types of computers in there. We can have different kinds of storage. FPGAs can serve co-processing roles. They can do inline processing for either low latency or high throughput processing. And then you also can have different kinds of front ends as far as your acquiring data and then generating data. So that covers the industry, right? From an industry point of view and from a market need, that's why we need FPGAs. But the problem with FPGAs is that FPGAs are an obscure technology. If you ask most people, they've heard of CPUs, they've heard of GPUs because of video games, but few people have heard of FPGAs. And certainly that is changing. FPGAs are becoming more and more of a popular technology. They're in the news. So a CPU is what runs your computer or runs your mobile device. It's general purpose, which means it really doesn't specialize in one thing or another. And because with a CPU we're writing software, it's instruction-based, we're writing software that ultimately becomes machine code. So that is a much quicker compile process. And now, even though CPUs have multiple cores, compared to some of the other processors, the parallelism on a CPU is really marginal. And GPUs, we have our graphics processing units. They, of course, they came out of, again, video gaming industry is what really drove it. And we have, of course, processing graphics, rendering graphics on your screen is what their main purpose is. And so at some point, people got the idea of, hey, we could use this, we've got this processor on a computer. Let's use it to compute different kinds of floating point math, specifically vector math. Because it's a software programmable device, we have quick compile times with GPUs. And especially modern GPUs, they have thousands of cores, so we can certainly consider that to be massively parallel. Sort of a drawback of GPUs is that there's limited interfacing. So in other words, a typical GPU can interface back to your CPU through the PCI Express bus, or it can then interface to a monitor where it can, HDMI or DisplayPort. Now, of course, none of these things are static. And if you look at one way to understand what's happening in the industry is to look at some of the mergers and acquisitions that happen. So if we look at, for example, NVIDIA has recently acquired companies that would make highly connectable devices. I think Mellanox is a company that they acquired recently. So I wouldn't count the GPUs out in terms of interfacing, right? This area is it's kind of a big land grab right now. It's a whole bunch of interesting things happening. And then that brings us to FPGAs. So FPGA is an acronym, stands for Field Programmable Gate Array. And the FPGA itself is spatial. You can see from the diagram off to the right, you can see that there's our logic blocks, which are in blue. And sometimes we think of those as a sea of gates. And those configurable logic blocks can have very simple math, or they can have something more involved, say like a multiplier or a DSP, and even in modern FPGAs, you can even have a CPU in there as one of these blocks. And in some cases, that can be memory that can be in there. That's what you can have in each of these blocks. And of course, each of these need to be connected somehow. So we have programmable interconnects. So based on the configuration, we can have each of these blocks connected to each other. And so by configuring the blocks and wiring them up using the programmable interconnects, we get a circuit. And we should really never forget that we're always programming, there's a circuit that's down below. And then, of course, there's I/O blocks surrounding the FPGA. So the I/O blocks allow for us to send signals and data into and get data out of the FPGA. So you can see that there really isn't the notion of a core. If we were to think of core, we don't really think of FPGAs in terms of cores, but if we did, we would say that the cores on an FPGA are reconfigurable and they're heterogeneous. So in other words, I could resize a core and I could have cores that are of different size and of different function, which I don't have with CPUs and GPUs. And with the GPU, if it has 2,000 cores, that's what you got. You get 2,000 cores. It's pretty much fixed. You can't resize them or reconfigure them. Now, FPGAs do they suffer from long compile times, and that's a really relative term, because if we think back on the earlier slide where we talked about ASICs have a 6 to 18 month development cycle. So an FPGA, certainly it's a lot faster than that, right? If you get a compile overnight, that's way faster than 18 months. So when we say long compile times, we're comparing that to software. And so in software, we have, you can get a compile in a couple of seconds or a couple of minutes. So these terms always have to be relative. And in fact, if you go in and read about EDA, the way that ASICs and chips used to be built, a lot of the things that we just click and tell an FPGA to compile, a lot of those things actually used to be manual, kind of like software. With software with punch cards, it was a highly manual process and very time consuming. A lot of these things have been, they've reduced the time for that. So when we say long compile times, of course, it's in comparison to the GPUs and CPUs. Now, as far as the interfacing on the FPGA, it's a flexible interfacing. So, modern FPGAs can have up to, over 1,000 pins. And traditionally, FPGAs are digital devices. So this digital interfacing would allow you to communicate to other types of hardware, right? So you can communicate back to a PCI Express bus, so you can communicate to your computer. You could communicate to Ethernet using some kind of like serial protocol. You can communicate to custom serial protocols. You can communicate to A to Ds and D to As or other kinds of circuitry. You could communicate to memory, like on board, you can have some DRAM or memory that you can have for storage or for buffering. And this is changing. We'll talk about this in a little bit. Notice that the term gates didn't even come up in that discussion. They're using the term logic blocks. The term gate doesn't even show up at all in modern FPGAs. But it's just a term. The term has stuck, and that's just what we call them. But the newer term that we're seeing, and it's not really replacing things, but it's just another way of doing things, is the system on chip. And a system on chip is a chip where you can have some of the things that I talked about, the memory and the A to Ds and D to As. Imagine all of those just being brought right into the chip. And so you can have a more efficient, the board can be smaller, you're using less power, and you can have something that's just easier to program because you can have it all from one place. You're programming one device, you're not programming and configuring a whole bunch of devices. Now, FPGAs, we said that they're an obscure technology, but they have a lot of other challenges. First of all, FPGAs require digital design expertise. And this is a specialty within a specialty, right? So you've got electrical engineers, it's one kind of specialty. And then within that, you've got digital designers. So it's electrical engineers that have spent their whole career specializing in digital design. So maybe they've worked on ASICs, they can work with FPGAs or programmable logic devices, right? That's their area. And so that there's a steep learning curve. It takes years to learn these devices and how to program them. And FPGAs were originally configured using something called schematic capture, where you would essentially take a schematic and fit it into the FPGA. And then that was sort of overtaken by something called VHDL and Verilog, which are hardware description languages. And we can see an example of VHDL to the right of the screen. And the challenge, so if you think about the way an FPGA works, it's spatial, and lots of things are happening at the same time. This text version of what's happening on the FPGA is may not be the best way to describe it, because what's happening is spatial and it's happening at the same time. How can I look at this diagram, this script, and know what's happening at the same time? Now, of course, an expert would tell you that. They would know that, but it remains as something that is not, maybe it may not be the best way. Now, to be clear, the majority of FPGA designs are conducted, they use VHDL and Verilog, those types of languages. So that does remain the sort of de facto way of doing things. Which brings us to something called high-level synthesis. High-level synthesis is a technique that attempts to make the design and working with FPGAs, give it more of a software feel, and to allow for more people to use and work with FPGAs. Now, with all high-level tools, we lose some efficiency, we lose some design control, right? So the things that the digital designers were used to and comfortable with controlling, they lose some of that. And so that's always challenging, right? When you go from, in software, you go from like assembly and you start using C, or you go from C into a higher level language. That loss of control is tricky because you need to, you're just used to that, especially those users. And then from an efficiency standpoint, that's certainly it's an unfortunate byproduct of this. But the things that allow for us to be less efficient is that the FPGAs are getting bigger, right? So as an integrated circuit, FPGAs benefit from Moore's law, or at least the observation, which is Moore's law. They benefit from that because we're able to fit more and more logic on the same chip. The other thing is that the projects, because the FPGAs are getting bigger and there's a increased demand on the things that we want to run on the FPGA, right? So the earlier FPGAs, you could just do just glue logic, whereas today you have a complex DSP happening on there. So now, a really complex, if your goal is to build something really complex, the traditional, more lower level tools could take a really long time to develop a system using that approach. So the high-level synthesis tools, certainly there's the cost of loss of design and control, design control and like efficiency, but you also get um, through that you also get you have the ability to complete these larger projects. Now, high-level synthesis does not solve the problem of long compile times. That's still with us. And so it's important to note that with high-level synthesis, you're still programming a circuit, even though it gives you this sort of software feel, and it makes it look like you bypassed all those challenges of VHDL and Verilog and digital design. It's a favorite quote of mine. It's the it's most known from Spider-Man comic. With great power comes a great responsibility. So just because we're able to point and click and change an FPGA and do something really quickly and efficiently doesn't mean that that doesn't need to be verified, and we don't have to think about what's happening behind the scenes. We do. And especially if we're working on an RF, radar, and electronic warfare application, by definition, even though the book has the term introduction in there, by definition, any system that is being used in that application, it's going to be advanced. So we need to be really aware. There's a bunch of things that we're going to talk about in a bit about that. So now there's many different kinds of high-level synthesis tools out there, and one of them is LabVIEW FPGA. It's it's a product of NI, and it's an add-on to the software development environment called LabVIEW. And so LabVIEW itself came out in 1986, and so it's a tool for engineers and scientists write software and control different kinds of instruments. But then in 2003, NI came out with LabVIEW FPGA, which allows you to use the LabVIEW environment or something that feels like the LabVIEW environment to reprogram and reconfigure FPGAs. So while some of you may just be hearing of LabVIEW FPGA, it is a product that's been around for some time, right? So 18 years, I would say, especially in the technology world, I would say that that's pretty mature. And you can see that from the different DSP options that LabVIEW FPGA gives you. You can see that from the different export options. You can see that from the hardware it supports. And I can tell you, because I sometimes, people will ask me, well, how good is LabVIEW FPGA, right? I mean, they're questioning like the high-level synthesis tool. My single answer to that has become, there's a product that NI makes called the VST, the vector signal transceiver. And this first came out a number of years ago, I think 7 or 8 years ago. And there's 2 generations of this. Now, this is a complex piece of RF hardware, and in both of these generations of the VST, its FPGA has been programmed using LabVIEW FPGA. And so when someone says there's a high-level tool, like how good is it? That's the answer. The fact that you can reconfigure and develop a complex RF piece of hardware such as the VST using LabVIEW FPGA, that tells me that it's certainly good enough to for a lot of these types of applications. And in fact, you can see on the lower right of the screen, you can see the part of the top level of the VST's FPGA, LabVIEW block diagram. And then on the top, we can just see just another one. So it's just from one of the coprocessors. So just some of the NI hardware that LabVIEW FPGA can program. So you can see all kinds of just more like OEM devices. You can see there's just different kinds of instruments, different kinds of DAC cards can be reprogrammed. There's software-defined radios from the Edis acquisition, and of course, different kinds of RF hardware. So it's pretty broad. And until recently, you could only program LabVIEW FPGA to NI hardware. But then in last year, in May of 2020, NI came out with an add-on to LabVIEW FPGA called the LabVIEW FPGA IP export utility. And this allows you to export your algorithms to either a netlist or to VHDL. And so you could use it on non-NI hardware. So this is certainly still new development, but quite exciting. And I guess we'll have to follow that. So now we've, just to summarize, like where we've gone, we've talked a little bit about the industry and the needs and why FPGAs are important to the industry. We've talked a little bit about the tools and FPGAs and LabVIEW and LabVIEW FPGA. So now we're going to look at the people side of things. So do LabVIEW FPGA users know RF, radar, electronic warfare concepts? I would say for the most part, they don't. And the book helps bridge that gap, but this is not meant to be this book is not meant to be make you an RF expert. I can, speaking for myself, I have always, past couple of years, I've been working with different RF engineers who, their background is just RF, and they help me understand various concepts. So that's always helpful if there's different colleagues or people that you know in your network to get to learn that. And so it certainly, the book takes it from a point of view of, okay, you want to solve this problem with LabVIEW FPGA. What are the things that you need to consider? Additionally, the book has a for further reading section. So it kind of takes you to some other resources. I mean, the book tries to be standalone, but at the same time, there's just so much stuff out there. One of my favorite resources was the MIT Lincoln Labs YouTube Radar lecture series, which is 25 YouTube videos, somewhere around like 30 to 40 minutes each. And it's really good. It's doesn't need too much background. So that's a good starting point. Then there's different websites. Radartutorial.eu is another really good one. And then there's just a whole bunch of books, right? I mean, that's just, it's not that there's a lot of books, but there are a couple of books out there that, are recommended. And so you can, there's DSP books, there's radar books. The Skolnick is a classic, as is the EW 101. And so, you just got to find the information where you can. But that is one challenge, is that you've got LabVIEW users and you've got LabVIEW FPGA users, and they don't all know RF, radar, electronic warfare concepts or applications. So that's one challenge that, another thing that we need to cover. Now, what about FPGA knowledge? We talked about the LabVIEW FPGA users, but what about the radar, RF, or electronic warfare experts? A lot of times they may not know about FPGAs. They may be just working with algorithms. They may be working with just, they just may know how to work with like boxed hardware, so they're just turning knobs and they can set things. I mean, they can understand signals. They can understand digital signal processing or just signal processing in general. So there's people, or they may just have like a MATLAB or a Python background, right? They're just writing these algorithms. So they will somehow need to learn FPGAs. And the one thing that's challenging with learning about FPGAs is that I find that there's resources out there that either give you too much information or too little. So with too much information, you've got books and resources that are targeting digital designers, right? So these are people that have been working in the industry for years, and it's a really specialized type of user. And if you go that route, you're probably gonna know. I know there's no such thing as knowing too much, but there is a limited amount of time that we have, so we do need to be cognizant of that. On the other hand, there's resources that just give you too little info, and so this is referring to like the hobbyists. They sell like these FPGA development boards. They're like, $50 or $20, and the joke with those is that you can blink an LED. You'll do all this work and then you'll blink an LED. But and certainly there's something to be said about learning that and just understanding the lower level tools. But that's going to give you too little info, right? Blinking an LED or doing something really simple, enabling a 7-segment display is you've got a lot more to go from there to processing high bandwidth RF data. So that's certainly a need that the book attempts to fill. There is a whole chapter on background technology. And overall, what I find is that you start with some FPGA knowledge, work on the project. As you're working on the project, you iterate. You go back to the source and you go back and learn more about the way that sometimes you may come across FPGA concepts. You'll get a compile failure. You get like something is not working the way you expected it. You can go back and learn more. And that's what I find is the best way. So some of the FPGA concepts that the book talks about, there's timing, right? So on the FPGA, we have to think about like our configuring clocks and configuring the different clock domains. Timing is a big part, and and if you can't execute at the right rate, you'll get a failure in compilation, right? You'll get a timing failure. And then we've got resource utilization. So the FPGA has a finite amount of resources, and we need to be able to make sure that what we have will fit within that specific FPGA. Now, before we actually go to the FPGA, we need to be able to model that, model what we're trying to do. So maybe in some other, like maybe in some kind of software is what that means. So like in MATLAB or in LabVIEW or in Python, some language, or in C, right? Just any kind of software language, you model out what's going to happen. So you have, you say like, for example, these signals are going to come in or with these parameters, and then this is what's going to come out. So we need to be able to model this before we start working on hardware. And then when we work on the hardware, we start to write things for the FPGA, because don't forget, we've got those long compile times. We need to be able to somehow simulate and just make sure that simulation can help save us a lot of time. Because, for example, let's say I've miswired to subtract functions, or I've not configured something, I've got the wrong data type. I want to be able to catch that early on. I don't want to have to wait a couple of hours for a compile and then see that I made that mistake. So that's the point of simulation. You can catch a lot of problems a lot earlier. And then sort of a little bit more lower level, pipelining and handshaking. Pipelining is a technique that's really important on FPGAs because you can keep as many of the resources working and running on the actual FPGA, not just have things just running sequentially. And pipelining helps us achieve higher compile rates, higher compile times. Pipelining can help us get higher clocks in terms of getting our FPGA to compile. And then we've got handshaking. Handshaking is where if we have different blocks on the FPGA that are running asynchronously, which is common, and we want them to be able to run as quickly and optimally as possible. So when they're sharing data, we want them to be able to message or signal to the neighboring functions when they're ready for data, so that way they don't overrun, they don't lose data, but at the same time, we want them to be able to run as quickly and as optimally as possible. And so again, the book has the background technology chapter is it's hard to say what's the right amount of FPGA info, but that's the goal of the chapter 3 is to get you the right amount of info. Okay, so that's the industry, the tools, the people, and again, back to kind of some of the concepts. And so now you can have a bunch of RF experts, you can have a bunch of LabVIEW FPGA experts, but there's something missing in that. Sometimes projects don't work out as expected, and that's because there is I believe that there's a product mindset that's missing. And now, certainly the term product, some people look at the word product and they think of cars on an assembly line, or you're making cell phones, just mass production is what they think of when they think of a product. And then the other thing is that the high level aspect of LabVIEW FPGA, the software aspect of the FPGA itself, makes some people think that this should be a quick change, or this development should be done really quick, right? It should just be done in a short amount of time, whatever that is. And overall, I think the product mindset, not having the product mindset, I think can have some built-in time and cost impacts. Now, whether we want to call this a product or not, that may be semantics. I think it's important to look at things from the perspective of how will we build the system. And that's interesting. You may look at this and say, hey, we're not talking about LabVIEW FPGA anymore. That's true, we're not. And we're not talking about RF anymore. We certainly are not. But this is a critical part. I've seen projects and trained people, and this is an important part of that. So now I'm going to give you 2 examples. The first example is going to be, I'm going to go through each of these questions with these 2 examples. So the first example, it's going to be, you've got a single researcher that is both the signals expert, and they've learned a little bit of LabVIEW FPGA, so they can also program. And they're going to build something. It's going to be a tool that they're going to use. It's not going to have too many levels to it, right? So it's not going to have sub-assemblies that they need to unit test and so forth. They're the end user. And in fact, when they leave the company, maybe that tool will be decommissioned, like no one's going to be using it anymore. It's their own tool to just help them with a project. So now, when you have things in such a sort of unified setup, right? Like one person kind of knows everything. We don't need to have the product mindset. And that person, I bet, will be successful because they know everything, right? And they are responsible to themselves. They will know how to sort of juggle things, and they'll do their own risk analysis. So in that case, yeah, all the stuff that we're talking about here is going to be overhead. On the other hand, let's say we have a project where there's going to be multiple developers working at the same time. This project is going to have multiple components, and we need to be able to test things out individually. And maybe those sub-assemblies will go into not just one system, maybe they're going to go into multiple systems. Maybe the end user is in a different organization or a different part of the country. So like they're not someone that you could just walk down the hall or call and just talk to. And in fact, the support will be taken over by some other team, right? So after your team builds this, it's going to be given to someone else to support. Now I know that I've exaggerated all these questions, but that's where we need to have that other discussion to look at the complexity of things. So in that case, if you don't have the product mindset, you are adding cost, and you are adding more time to the way you do things. And so we don't have to develop these things from scratch, right? Like there is the systems mindset. There's something called systems engineering. It's a whole field unto itself. This tells you all about that, right? I didn't need to, I referenced this in the book, and I talk about this and use these approaches, but you don't need to, this is, it's all out there. The trick that I find is to know how much of these concepts and techniques to use, because these systems engineering is made for building a whole, aircraft carrier. And so I don't think we're doing that just yet, right? We're doing something a lot simpler compared to that. But still, the systems engineering approach, we can pull from it certain techniques that can help the project be more efficient. Now, in a nutshell, a systems mindset is where you take the whole system and you break it down into subsystems. And then you take those subsystems and break them down into components. And then you break those components down into elements. And you may have to keep breaking things down until you have sort of fundamental pieces that are, everyone understands what they are. Because if someone says to you, hey, go build this thing, go build this radar tester, that's may mean different things to different people. But if we break things down into each piece, then we can have a better understanding. We can then define the interfaces between all those pieces. And those interfaces allow for us to define how we're going to test and verify those. So this is important when you're building any kind of system, when you're building a LabVIEW FPGA-based system or any kind of FPGA-based system, because you've got the long compile times, because you've got things that can go wrong and it's really hard to debug things. Well, those are problems that we have, and this is one way to help mitigate that. So about process, we've got people talking about Agile, and we've got people talking about Waterfall. Maybe less people are talking about Waterfall these days. But just like the product discussion, I think this also can be it can be semantics. We can get caught up in just the label. I've seen that the drawback of the Agile mindset is that we try to just start coding right away. And especially with LabVIEW and LabVIEW FPGA, that's very tempting. The tool is graphical, it's kind of fun to use, and you just kind of jump in and start doing things. But the thing is, if you start to do things without the big picture in mind, that goes back to the systems mindset. You may do things, you may make decisions in the way you're coding things that will have downstream costs. And so again, sometimes we'll say, well, we'll fix that ourselves. We're the ones, we'll eat the cost, we'll figure it out. But if we keep making lots of those little decisions that sort of add up, there's a lot of cost that ends up being, gets added into the system. And the question is, so the Agile approach, I think, was developed out of, Waterfall was just very costly and had failures. I get that part. I'm not trying to pit us against one against the other. But the thing is, sometimes when we're building a system, we know there's a lot more than that we know about the system up front. And knowing those things up front, we should be able to ask those questions and understand more completely what we're building. Now, LabVIEW and LabVIEW FPGA get used in a lot of research environments, and that sort of research, the research mentality, which you don't know what you're going to find, you don't know what's going to happen, sometimes gets carries over into the way LabVIEW gets built, or LabVIEW FPGA tools based tools get built. And I think the key thing is to be able to sort of separate that. Let the research be the research and let that have its own uncertainties. But when someone says, hey, we need a tool that's going to do this, we need a tool that's going to generate different kinds of signals, and it's going to do, it's going to play back a whole bunch of signals, we know what that's going to do. We shouldn't act as if there's some kind of surprise down the line. And I'm not saying that things happen perfectly always, but I think the key thing is to resist the temptation of just jumping right into coding and just building things, because that gives and I know why that happens. That happens because there's the perception of progress, and sometimes that can have drawbacks. Anyway, there's a presentation from Steve Watts from the LabVIEW community. He's also another author, and he gave a presentation a long time ago talking about risk management. And I went out and bought this book. It's called Waltzing with Bears, and it talks about managing risk on software projects. And I can tell you from my own experiences, documenting and the mere writing out of the different risks it's good to get that all out there, because most engineers and managers, they know what the risks are, but by not writing them out, I think that there's an element of we're kind of saying there's an element of ignoring the risks, and that could happen. But I think there's a big problem there, because sometimes we know what the risks are, or maybe we know just the risks that we see. But by not looking at what all the others are, we end up focusing on what we think is the big problem, but maybe that's not the project's problem, or maybe that's not the team's problem. So that's my favorite quote from the book. Talks about risk management being project management for grown-ups. Okay. Now, we've got LabVIEW FPGA, we've got our know-how of RF and radar and electronic warfare, but then there's a bunch of tools that we need to consider in addition to LabVIEW FPGA. And here I list out a couple of tools that I find to be very useful. In parentheses, I've got examples of some of these tools, but certainly you can use any tool that, there's a lot of other alternatives. So the first one is some kind of document management. Some projects, you'll see that the documentation sits in people's inboxes. And this is terrible, because I don't have the latest document. I have to wait for someone to email that to me. And after they email it to me, they start to work on it and they make changes. And there's lots of copies of the same info all over the place. And there's no sort of centralized way of keeping that information organized. So a tool like Confluence, for example, it's made by a company called Atlassian. Confluence is it's a wiki. On the surface, it's a wiki, but it also has a lot of collaborative aspects. We track our meeting notes in there. We have our decisions. We put a lot of our diagrams in there. And so we also have like an internal knowledge base using Confluence. It's really useful. Then we've got different ways of different design tools. Now, again, some people you think of LabVIEW FPGA and you say, well, the design should just be in the code. I should just be able to look at the code, and the code just tells me. They use these terms called self-documenting code, which I know what that means. That means that the code itself has function names that are understandable. They have variable names that you can understand, and from panel objects that you can understand. But that is not the design. The design, a lot of times you'll have people working on a whiteboard. They're working in Visio. They're working in some kind of other place. And tools or language, modeling languages such as UML allow you to have different views of a system, right? So LabVIEW can give you a couple of different views, but there are views that it just can't give you. And the other thing is, once you're in the development tool, even though LabVIEW doesn't have a lot of syntax, you start to, there's a perception that, oh, this all has to function. It's not good unless we make it, let's finish it, let's get it running. But meanwhile, there's something we need to do before we start to use LabVIEW. We need to start doing some kind of a design and kind of map things out. So for example, among the UML diagrams is the sequence diagram, and that shows different sort of lifelines and different items communicating to each other. There's no way you, and that, so I could get a whole system on just one diagram, and I can show all the messages that are going back and forth and all the data that's going between them. I can't see that in any other place. And now another benefit of these design tools is that you can have a phone call with someone and say, hey, you're going to go build this, and they're going to have one thing in their head, you're going to have something else, and they're going to go build it, and you're going to look at it and say, that's not what I wanted. Meanwhile, you were both on that same phone call. You both talked to each other, and you know each other. You've been working together for years, right? Like all those things have, you know, there's no strangers here. But the design tools are more ways that you can sort of articulate and describe what that should look like, what you're looking for. So there's a lot of benefit to that. Myself personally, I used to think UML was for these large enterprise systems, and it was just a lot of overhead. But it's, again, kind of like the systems approach. If you pull in the right tools and the right pieces, it can be very useful. And then we move on and look at issue and task tracking. So tools such as Jira, which is a task tracking tool also made by Atlassian. But there's other task tracking tools you could use, like project management tools. Some people, they keep track of their issues and tasks on a notebook, or they keep it in Excel, which we know Excel wasn't made for that. And that certainly is a good place that you could start out by keeping track of those tasks there. But there's no collaborative aspects to a paper notebook or to a spreadsheet. And none of these tools have sort of the ability to track the life cycle of a task or an issue. And so there's tools out there that do that, right? So why use the, you know, they always say you shouldn't use the, you know, you should use the right tool for the right task. And so we should be using task tracking. Now, all of the above items on a project, some people can debate whether or not they need to use them and if they're important and so forth. But source code control is, I think that's one of the most important tools here. Source code control gives you a backup system. It gives you it allows you to track versioning of what you're working on. And it's a funny thing because in the LabVIEW world and the LabVIEW FPGA world, unfortunately, people actually debate whether they should even be using source code control. And if you said this to a non-LabVIEW person, they would think you're, you know, what are you talking about? That's not even a discussion. Like in the C or C++ world, they don't even debate that. But unfortunately, it has to be emphasized. You know, it is something that, you know, let's put it this way: the minute code starts changing, source code control should be used. I worked on a project one time where we were just trying to figure out the configuration. We really weren't doing development, right? We were trying to sort of understand things. But while we were doing that, code was changing, right? So technically, maybe we were in development. We were trying to mitigate some risks, but that code should have been saved somewhere. And we of course, we were saving it. We did use source code control, but some of the team members were against it. They were saying, well, we're not in the development phase. Source code control should just be used when we're doing development. And the answer to a lot of that is, you know, how much is your day worth, or your work? You know, you work on something, and one day, and you work on it another day, and you lose some of that work. You should think about that. Source code control will help with that. Now, some people have zip files that they put on a server. They rename them. This too, it's unacceptable. You should use source code control. There's so many tools out there. There's free tools. Their cost, even the ones that you have to pay for, the cost is really low. So that really shouldn't even be a discussion, but we do need to emphasize that. And the tool that we like to use is Git. Git allows for a decentralized source code control. And so it allows for people working on machines that aren't on the network, which may be common in some of these RF and radar applications. And Git allows for, you can then have people not on the same network, and then you can have merging of some of those branches. So it's sophisticated. It has a lot of abilities, but there's no shortage of information online on tools like Git. So now the last tool that we're going to talk about is called the build server. Some people call it a test automation. Some people call it continuous integration, continuous delivery. Just has different names. I just call it by build server. So now let's say you have a project where you've been working on it for a year and it's got all kinds of code and all kinds of pieces, and you now need to make a quote unquote small change. It's going to take a few days. And so now you've made that change. How do we know that we didn't break anything else? Well, we're going to test it. So we're going to go through and run through some tests. Now, for such a big system, testing may take a couple of days. It may even take 2-3 weeks. So imagine that. A small change that took a few days now takes, actually, the change itself took a few days, but then the completion of the change, because it's not done unless we verified everything, let's say it takes a whole month. And so at times like that, we start to see that things are, that's really inefficient. I mean, the change, the inertia of the project just becomes so big that at some point it just, it's at a grinding halt. It's hard to make all those changes. So a build server, something running a tool like Jenkins or Bamboo, can automate those. And you can have either compiles, like LabVIEW FPGA compiles could be running overnight or even all the time. You could have different modules being tested. So that way, if you do make any changes that break something else, it'll alert you to that. Now, these tools can be, they're highly configurable. So you can have your own configuration environment for each project you're working on. You can have, like using virtualization, like virtual machines. You can have them run these tests or these compiles either continuously, or you can have them running these tests based on some kind of a trigger. Like someone pushes some user says, okay, we're done, run the test. They just push a button, all the tests run. It could run based on a specific kind of change. It can run based on periodically, we can say, okay, at 1 a.m. every night, we're going to run all these tests. So this wraps up the motivation of, why write this book, right? And so the book tries to pulls together a whole bunch of different things. Again, so there's some talks of industry and application and sort of the market. We do look at some of the other FPGA tools that are out there and why the NI FPGA tool is a very mature tool among the reasons mentioned here. And then we look at the people. Not only do we look at the types of users, the users, but we also look at the types of users that are going to be using LabVIEW FPGA, because different things will resonate with different people. But we need to sort of consider all of that in the book. And then we talked about building it. So building it, you got all the experts in the room. You do need this sort of product mindset or a systems mindset to be able to bring all that together and not miss anything as you're doing this.